Hello, everyone. So it's really hard to go after John, but I'll try my best to fill the shoes and keep up the sort of the temperature here. All right, I think it's a mouthful of a title, but really you should just remember EdgeRig. And next time you want to see what we are doing, just Google EdgeRig, right? It's very catchy and simple. So I think I want to acknowledge all the collaborators. I think 2019, it was COVID. I think I got together with Srinivas Shakota and we were like, hey, let's do something together, right? And we started doing some schedulers and then we came into designing this EdgeRig effort, right? I think so many students have contributed. At this point, we also have almost 100 users for this platform, right? So feel free to download and try it out. So let's take a look. I think, and I'm glad I'm like so good in after the afternoon in the sense that everybody has already talked about the importance of real time and understanding of real time and how we should sort of go from NextG becoming sort of from more connectivity to an entire infrastructure provider. So this is something which a transformation everybody should sort of support, right, and push forward for, right? So with that, I'll try to maybe push a little bit faster through this right part. So I think we are all seeing a lot of these applications where we want to have these thin glasses from there to a lot of robotics and AR, VR, where cloud gaming, these are really driving a lot of user traffic and will continue to drive. Actually, we have a very interesting study where we noticed what is the largest usage today on the phone or 5G network. And we found a very polarizing result, right? For some people, the usage has gone down over time. And for some, it's just gone so dramatically up. They use Instagram as the highest traffic is sort of interesting. And also obviously tools similar to Instagram have become really dominant traffic, right? So these traffics will remain, but there are lots of these traffics really starts to diverge from quality of service, right? So traditionally we all as a network builders from 5G to 6G, we sort of focus on quality of service and try to guarantee those things, right? But these applications are now becoming so diverse, they need something called quality of experience, right? This is what you can call it UX, UI, or sort of different sort of things people have referred to, right? How do we deliver those with these next-gen networks is really going to be the fundamental paradigm, right? And we have looked at lots of use cases on this, right? And I'm going to skip some of this because a lot of people already have before me explained this, right? And Edge is going to be the key driver of all these next generation application, right? And why I say that, and I'm gonna maybe make one concrete point here really, and try to flip through this a little bit quicker and get to more interesting details on EdgeRig side. But really what's happening and what we are seeing is, this is a singular message. If you go back and to talk about what I'm working on is sort of enabling tokens at low latency. And this really will be first grade revenue driver for NextG, right? And I say this with a very, very caution. We are at the sort of saturation of how much revenue we can get, or the network providers and the entire ecosystem which supports our research essentially is bottlenecked with the number of subscribers. And these subscribers are flattening at this point in time, right? And the telecom providers and the entire infrastructure should sort of translate into becoming infrastructure provider where they provide GPU compute or compute at a lower latency timescale. This is going to be a fundamentally new way for us to drive revenue and also make sure our ecosystem prospers and more funding for us in research, right? Okay. So this is like one single message you want to go discuss in the audience after the break, go discuss this part, right? And how you can drive more things, right? And the one thing which I have very, very clear, like if you take one thing away from service industry today, it's that they have so many open source tools and these tools get so fast adopted. It's like you look at MCP, right? And the number of stars associated with an MCC open source project, it's amazing, right? I think we at the cusp of this audience here really has to really drive the same open source ecosystem around lots of, let's say, connectivity modules we already have. How do we tightly connect them with the compute modules and deliver new sort of experiences and services? Really become the fundamental driver of next generation sort of revenues, right? So with that, I'm going to now speed up a little bit and go into a little bit more, let's say, network-centric things, which I'm here to present. So this is our traditional deployment strategies for next generation RAN. You have RU, DU, CU, and core network. And then there are different types of RICs, which are RAN intelligent controller. The idea of these things is that they are decoupled from the RAN, but they provide the necessary intelligence you want to drive new use cases, right? I think in recent forum at IORS, Ericsson announced around 30 plus apps they have from different vendors in non-real-time RIC. So that's already a great thing that a lot of vendors are driving the ecosystem, and hopefully they'll come down to near real-time RIC and something more crazier and cooler. And I'll try to make a statement why should they do something more cooler than that, right? Even near real-time RIC. So what happens is that these near real-time RICs and non-real-time RICs are great for doing macro level optimization across networks. At a very, very fine, very slow time scale, you can do lots of cool optimizations with these things. And the reason for that is that the latency associated in their intelligence. That intelligence comes at tens of milliseconds. That's like million years in the world of wireless, right? Okay. And let me give you an example why this is million years, right? And I'm sure I'm not saying something new. Everybody in the audience, and this is what I teach in my class as well, the channel coherence and the stability, I call it differently because just coherence is so crowded term. The point until which you can take channel and predict until how far in the future is very short in the world of wireless, right? On the other hand, our intelligence sits on the left side, which is far away from really the action where it happens, right? The channel changes so fast, any reaction you have associated with this will never sort of work in this use case, right? And this is really where all the problem lies, right? So how do we support these live adaptations? The way to support these live adaptation, and this was something we thought was crazy. In 2019, Srinivas and I built together this real-time RIC. It's called EdgeRIC, right? Or we named it later EdgeRIC, right? Because that sounded cooler. But back then we would call it real-time RIC, right? And the idea is that it gets information from the DU level at less than 100 microsecond, right? I think we can do actually 10 microsecond today, right? And then you can do a lot of your AI ML apps if you want to, and decide doing cross-layer optimizations and all the things and send those actions back to this side as well. And this you can do in like 20 microseconds back and forth. You have around 480 microseconds, depending upon the slot time you have on the TTI side, to give you interesting apps which otherwise are not possible, right? And the great part about decoupling this intelligence from the RAN, which is very much the same for these things, is that this will keep functioning. This has to be a high reliability, high performance system. Even if this crashes, this can continue to operate. So this is a built-in resilience system on this end, right? Actually, there is a lot of philosophical question. I had discussion with SoftBank and several others on AI RAN related things. Why not package AI into the RAN itself, right? And the philosophy, at least I think, is that this is too risky. This is a very safe way to sort of inject intelligence without breaking anything in this side. So with that, I think this was the first sort of primitive as to you want to handle dynamic channels. And the way to handle these dynamic channels is really take actions at a very, very fast time scale. So the second thing which we did, again, this was 2020, right? I have not changed these slides a lot from there, right? The point is, how do we, I think there is a lot of discussion on context and providing context about applications. I call it application awareness. I think back in 2020, we tried this and we were like looking at video content delivery, right? For example, you are on your sort of car driving and you're trying to get some streamed video and you run into an outage action event. But the problem is that network never knows that you're about to hit an outage. So the way network works is that it's trying to maximize network throughput. What it means is really, it tries to prioritize user with higher channel, generally speaking, right? And in that case, because your channel is weak, even though you're about to hit an outage event, it will not prioritize you. So that means you will get into a stall event. So this is where we came in. And we are like, let's build this application, right, with application awareness, right? So for first, we took video content traffic still remains the mainstream. 70% of traffic goes through video, and that's the main use case. And we showed how do we get edge servers to give intelligence and app awareness to both all the RAN intelligent controllers, right? The near real time, the non-real time, and our edge RIC, right? And this essentially is built with a complete Redis and lots of cool scaling facilities. It can be deployed in distributed manners. It's all Dockerized, containerized, and it supports Python ecosystem. So you can write all these micro apps in Python. And this actually, one single change in our architecture choice has driven 100 plus users, right? A lot of people really want to see, they want to build new schedulers. They have a lot of strong background in schedulers, Python, and information theory, they do not have as much systems background. For them, this turns out to be really clean way of trying lots of their new schedulers and driving some new cool ideas. Ourselves, we have built a reinforcement learning based agent and sort of have shown extensive improvements on this. So this is already open source. It's already been out there. Go try it out, right? It provides you with application awareness. It has some standardization defined across different apps, and we are increasing the apps we use every day. There is a lot of dynamic environment we can handle here, right? And it's close to store Orion standard compliant, right? And there is a lot of papers across the dimension right now going on for this, right? Okay. I'm going to focus on this application awareness. There is a lot of work on security and privacy and a lot of end-to-end energy optimization on both user side and the base station side. And we are looking at a lot of NextG for AI and AI for NextG. I think John had this one slide where he summarized all the variations of AI you can apply with the networking. You can sort of imagine all those things. I think I see a lot of engagement from Singapore, Japan. People are using this extensively as our platform goes. So this started in 2019. We wrote first paper on this in 2020. It took 2 years to build it. There is other proposals from even Microsoft, Janus, right? I think now that is also, we are going to become the maintainer or something along those lines for Janus effort. I think Microsoft has open sourced it. And this was also tested with a lot of commercial stacks from Radisys and other vendors out there, right? So that proves whatever we built on top of it can easily be translated into real use cases, which out there driven by public 5G type of use cases. So I'll try to summarize this in a very, very quick, condensed manner and show you a demo and try to leave with questions and save some time if possible. Let's see. So this is a way how you use today the EdgeRIC, right? You have entire vRAN softwareization plus EdgeRIC sort of is deployed right next to it. It can be in the same sort of compute server. It can be in a nearby compute server. It has to have some latency tolerance, right? But it just takes 1 or 2 core on any machine, right? And it gives all the intelligence. And funnily, interestingly enough, we found that a lot of models we were running were small models. And all of those model runs more effectively in CPUs instead of GPUs. The problem is that the time you carry the data over to CPU to GPU, the latency you eat up is so high that it's better to just keep into CPU and just do computing on there. So some interesting fun things. Here we first started building, let's start building some of these reinforcement learning models. The problem with these reinforcement learning models is that they tend to sort of not converge very easily. And you have to have repeatability in the environment. And this is where, if you start doing real world, that's what I do a lot more. The problem is that you cannot guarantee the same channel play over again and again to understand if there is a convergence in this side. So we came up with first tried 3GPP statistical channel. They are really problematic. They don't do space and time coherence, right? So you want to not use them at all, right? Or you just want to use them for different use cases, not at least for training these type of use cases, right? Siona is good, but still not accurate. Wireless and slightly more accurate than Siona, but still fails to get complete accuracy. So we trained our models first, starting from this, then this. The ray tracing models sort of helped to get initial convergence. Once you have initial convergence, you keep replaying the same real world data again and again until you see some convergence, right? And we have collected lots of real world channel data right now from both indoor, outdoor, extensive environments, right? And you can all go plug and play those, build your own schedulers, try simple schedulers and see how they work on real world use cases. Then we also have created a lot of software UIs where you can create different traffics. We'll see a lot of demos tomorrow as well, where we have lots of robots and other things where you can really run in real time the use case and test it, how it works in the real world as well. The reason I call it Tiny Twin is this entirely is built on an x86 based accelerator. And this allows us to run this twin at, like I can run 1,000 tiny twins at the same time and run 1,000 reinforcement learning model, converge in a fraction of a second. If anything, I can pretty much train an online model in real time given enough compute, right? So imagine if you realize that the channel has changed significantly, something has gone wrong. You can take all the past data and train a new model pretty much in hundreds of milliseconds in this case, right? So that just really creates a great sort of way of doing this. So this is something where one use case which I find has a lot of dual use everybody from military to real sort of users love it. You have a drone, and this drone is controlled by some of the videos I think earlier Modal AI showed. A controller, remote operator, he wants to send these commands. These commands has to be delivered to the drone. And in near real time, he wants to see the feed and the change in what happened, right? Is there an intruder? Does he have any better, or he's a bad actor? Is he creating any problems? This goes from all the way to teleoperation to cloud gaming. All of these use cases pretty much end up sort of going into this motion to photon latency behavior. And what we notice is that if you do quality of service optimization in this, right, okay, this suffers and it doesn't do well, right? So just to give you this, is these two schedulers, right, most are really application aware but traditional schedulers. And this is our reinforcement learning. And you see the stall duration created. We created a heavy workload, lots of robot trying to sort of have a file downloader user as well. And the network has no awareness and it just ends up really making poor decisions, right? And once you give awareness and you start using reinforcement learning, you start seeing significant improvement in the stalls. Now let me show you a real video and real demo of this, right? And here is a screen of this operator, right? He's sending these commands and he has a 5G dongle. All of these commands go through this 5G dongle to this G-Node B base station. It's running an open source SRS RAN base station. And this has other user, which is this robot. It has 5G dongle. It has camera and LiDAR. These are camera and LiDAR data frames, which you see on this user screen. And I'm also showing it on the inset so that you can see in real time the delays and the lags, right? And here I show the network throughput, right? In the beginning, I'll just connect this drone or this robot and this particular remote controller only to the 5G base station. And later on, I will add a file downloader use case, which will essentially spike up the throughput. And you'll start seeing the screen lags, right? Let's see the video for a minute, okay? So you have the G-Node B, right? As I explained, the traffic is rerouted on this side. So now you see the video saying when you have this is very instant reaction. As soon as this person moves, you see instantly changing. Now we'll add another user. This throughput will go up. It's just really an EMBB class type of traffic. And you'll start seeing this guy is moving controller, but this screen is updating after he does all the movements, right? And now he will try different schedulers, right? And you'll see the lag still goes on. Now he's gonna turn on our reinforcement learning scheduler. It increases, spikes the throughput in a little bit, right? But then it figures out what it has to do. And now you'll see pretty much instant reactions back, like you saw originally in that. So this particular scheduler is extremely application awareless, and even in 100% traffic load, it can essentially handle these situations, right? So with that, I'm gonna just summarize. There is a lot of question I get when I present EdgeRIC. Do you really, really need this type of real-time intelligence, right? Why not do it at a lower time scales, right? And I'm showing 3 examples, which I think are really representative. We can see clearly we can do much better in throughput from network throughput of 20 to 30. It's 50% improvement if you start doing real-time control versus near real-time. If you start looking at reinforcement learning convergence, you can see the convergence itself is so poor for these types of reinforcement learning if you start to have a lot of delay. Finally, you can also look at the end-to-end quality of experience metric, and we can show that even in that case, our reinforcement learning based mechanisms beat significantly, or this is actually essentially showing this result in some sense, but it kind of gets you even stall durations and lots of other things much more done effectively compared to the near real-time rig. So I think I can go into more details of how this entire thing is done, but I'll let you continue to read the papers, and these are some nice figures showing how you can synthetically scale up our simulations and run it in a really fine time scale. You can span up 1,000 Dockers and containers, and they can train different reinforcement learning, and you can see each one of them if they are training really fast or not. We have a large test bed right across the wall here, and this is courtesy of Ramesh. I think it's also something you can rent if you really want to. It has tens of software-defined radio. You can span up a rack of servers if you want to. You can span up a lot of 5G, DU, CU, CNs, right? We have Amarisoft UE emulators. You can run different types of traffic. You can have a lot of application edge servers, lots of 5G modems, right, on real phones all the way, and lots of Foxconn and high capacity network aerial type of setups available. So this facility is entirely available for all of us to use if you want to really. And I'm going to skip these are a lot of traces we have collected, both indoors and outdoors, all openly available for you to try out, right? I'm going to kind of skip and maybe just, given the 1 minute, I will rather not look at all these things, right? And I just want to just summarize with this one nice, cool video.
Multimodal robot
This is
platform. We have multiple cameras. We have a LiDAR and a depth sensor with infrared cameras. This is the compute. It also has a battery powered. This is the Quectel modem which connects to 5G. On this side we have a Wi-Fi modem which connects to Wi-Fi. The Quectel connects to the 5G network over here. As you can see,
this is the same lab I told you earlier
5G
about.
Network. This is the base station. On here we have the control server. We can.
So it essentially shows you real-time streaming of that drone video from 4 cameras, 8, all of those sensors. You can do Wi-Fi, you can compare Wi-Fi versus 5G. You can lots of these other use cases, right?
You can control the robot through the command line. Here. Can you control it, and I will see that it is moving.
Yeah. So if you want to see, you can just go during the break right end, and I am out of my time, and I will stop at that. Questions? How do I pause this?
It's updating live.
Okay. Questions, if any? Yes.
Thank you, Dinesh, for the very interesting presentation. I do have one question on the platform you're using.
Yeah.
Later you mentioned it's a SRS RAM.
Yes.
Is the platform. But I wonder whether the Edge rig is to replace the scheduler, Mac level scheduler, so you supply some kind of information.
Yeah, great question, right? So what we do is, I told you about the resilience, right? What happens is that the RAN actually is running a proportionally fair scheduler all the time. We adjust just the weights of different UE and different bearers, and that's how we make sure. So even if Edge rig crashes, the RAN has proportionally fair scheduler, which I think it does, like whatever human design, the best human design it has, it keeps running that, right? And so we have found that seems to deliver the optimal performance. If you did replace the entire scheduler with our reinforcement learning versus if you did the proportional fairness and put these weights in, it does very good. And we use something called Whittle index-based schedulers, right? And these are very popular indexing, and we prove that. And this is actually Srinivas and his great work, right? I think, and I see his colleague here in audience as well, right? And we can prove that a lot of these traffics are indexable. So you can come up with a lot of reinforcement learning based on these neural index type of strategies, right? So that's, it's super resilient, and that's how it's sort of built right now, right? Yeah.
Thank you. Maybe a follow-up. Then, I think that's great. Then have you guys tested it, how it generalizes? Across different schedulers, what you showed is I guess a non-massive MIMO small cell kind of. If it's Ericsson, massive MIMO with MU MIMO.
Great question, right? I think
how does this
my argument is reverse to you, right? Which is that, I can get more knobs and control variables, right? Like I would like to really control MCS coding and a few other things and how the resource blocks are allocated as well, specifically. We haven't gone to that level. But the point I want to make really is that we are operating at full load, right? And even in full load, we can do all these cool things, right? Which proves to our point that if I even get to the massive MIMO type of setups, right? And if you're willing to give us the access, I'm more than happy to try it out, right? And show that these things would still work, right? And it would, because I think the point really is it's all about, like, are we operating at full throughput or not, right? If it's operating at full throughput and you can still show this intelligence of prioritization, how you figure out what to do, that just shows that this can work even at massive MIMO scale. The question really is the load, really. And happy to be proven wrong as well, right? And or explore more research ideas on that. That's a great question. Thank you. Yeah, I think I'm glad. Yes, go ahead, Bryce.
On your example on altered video and the outage prediction, you cast that as sort of a scheduling problem. So you determine that the user's going to go out, therefore you schedule them more resources. generally I've seen that formulated more along the lines of an application problem, where the application has to go and say, hey, give me another chunk so I can fill up my buffer. Did you have to modify both, or did you find that the network was actually a limiting factor?
Actually, great question, right? I think giving this application awareness has been forever a problem, right? And I think there is a different political battles aside, right, on this topic, right? Like, any case, I'll come to the funny parts, but let me answer your question more crisply. So the idea is application/edge server shares the information directly with the edge rig, and that's how we kind of know that the last time edge server sent this much buffer and this particular user is now about to time out because he has not been scheduled since then. And now, therefore, we should really, really focus on prioritizing this user, right? So that's at least how the intelligence goes through. So to more precisely, it's all on the server side. I wish I could get a lot more user to share information. That would even cut down my latency of application awareness. So right now, my application awareness comes at slightly delayed path. But it's okay because application state changes so slowly that it doesn't matter. Actually, we have an interesting work with somebody in a control theorist, Jorge Poveda. He's a colleague. And he actually has been recently working with me to prove that where you can tolerate delays and where you cannot tolerate delays, right? And where will the queues blow up or the packets will start dropping within the entire network, right? So I think to answer your question, we have a application state coming from the edge server. I think if Apple, let's say, for example, enables somehow to share that application state with the RAN, I would have ran application state much more quicker than I could imagine, right? And then it would be really amazing, right? On that note, right, the way right now EdgeRig is transforming is now we are becoming edge computing platform. So even the edge server right now sits into the EdgeRig itself. So now the coordination becomes much tighter between the compute or the application server side and the networking, right? And EdgeRig is becoming a conduit to even computing, right? And we are really hoping to work with a lot of vendors and across vendor create sort of a common ecosystem where everybody uses just EdgeRig to build both edge applications and even network application. So you don't have to learn new things every time, right? And the great thing is that it's already integrated with OpenAI Gym and lots of cool projects already out there, right? And that allows you to get a massive customer base, right? And so that's something going on.